In this video, we're going to discuss the method of reduction of order. So the method of reduction of order is very handy when you're given one solution to a second order homogeneous differential equation. And from there, if you have one solution, you can find the other solution. And so consider the differential equation y double prime t plus pt y prime t plus qt yt equals 0. Now assume that we're given, assume we know y1. So we know the first solution. To the differential equation, but we're trying to find another solution in order to give us the general solution, right? Because for the general solution of a second order differential equation, you need two solutions that are linearly independent. So if we have y1t, then finding y2t is easy. Well, easier than solving it other way. So like if this differential equation does not have constant coefficients, so it's going to be very hard to solve this. So if we already have one solution to the differential equation, then we can find the other solution relatively easily. And so what we can do is we can search for the second solution. We can say that y2t is vt y1t. So vt is not a constant, because if it was a constant, then that means that y2 and y1 are proportional, right? And so therefore they're not linearly independent. They cannot form a fundamental set of solutions, and therefore you cannot have a general solution, right? So therefore vt cannot be a constant, and so vt is some unknown function, right? So we're multiplying v1t by some unknown function. Vt is an unknown function. Okay? Function. There you go. Vt is an unknown function. So now we know that since y1t is a solution to the differential equation, then if I take this differential equation, I know that since y1 is a solution, that this would be satisfied, right? Since y1 is a solution, this is satisfied. So we know this. And so in order to come up with the derivation of the method of reduction of order, we need to use this. And we'll use this in a second. So we know that, and that's great. That's a great start. And then what we want to do is we want to get a first order differential equation for v prime t, and so let's talk about that. So we know this guy. We know that y1 is a solution, and we know that y2t, by the way we've defined it, is vt y1t, right? And then if we take the derivative of this again, and so what I'm trying to do right now is I'm trying to put the derivatives of y2 into this original differential equation. So y2 prime t is going to follow the product rule, and so then we're going to get v prime t y1t plus vt y1t prime. And then we take the derivative, the second derivative of y2. So again, product rule, this time on the first term is v double prime t, y1t plus v prime t, y1t prime. And then now we go on to the second term. So then this is again product rule, v prime t, y1 prime t plus vt y1t double prime. Okay, and so now we can group some terms together. So these two terms are the same, so we can group these together and we can rewrite y2t as v double prime t y1t plus 2 v prime t y1t plus vt y double prime 1t. And that is your simplified y double prime 2t. So then now we have these three equations that we can plug into the differential equation up here. Okay? So if we do that, if it copies and we bring this down, we know. So what I'm trying to say now is we're going to prove that y2 is indeed a solution of the differential equation. So if I plug in what I know for y2t up here into the differential equation, then I get this, and I'm going to put this in white brackets, plus pt, and then y2 prime t, which is this guy. So if I again copy this and then put this in here like so, that's pt, and then plus qt. I had to bring this down because I'm out of space. y2t, and y2t is just vt y1t, right? And now this whole thing equals 0. Great, very good. Now what we have to do is we have to group a few like terms, and we have to use this fact right here. We know that y1 is a solution, so let's try and use that. So if we combine it in a specific way, we can actually get rid of that term. And what I mean by that is, we know that let's see, if we group the VTs, right? So VT, VT, and VT. So if we group these three terms, VT y double prime 1t, and I should put the VT in a bracket or outside, so V1 prime t plus Y1 prime t plus Y1 t. Oh, and sorry, there's coefficients that these multiply with. So this term, the second term, is going to have a pt, and then this third term is also going to have a qt, y1t. Okay, and that's the first term. And then your second term, we can say that that's v double prime t y1t. We can get rid of that, and then we can say that we have these two terms where it's just v prime t and v prime t. So then v prime t, and then I can just move this kind of to the side like so. So v prime t is 2 y1 prime t plus pt y1 t, and then this whole thing equals 0. And so now remember what I said up here. We're going to use this fact. Let me change this color to green. we need to use this fact. We know y1 is a solution, and the solution therefore is equal to 0. And we grouped it in such a way where we have the same thing up here and we have this here. So we can, this equals 0. So this whole first term is equal to 0. And then v double prime t y1 t plus v prime t 2 y1 prime t plus pt y1 t equals 0. All right, and now if we try and solve this, this is going to be kind of hard to solve. So we're going to have to make a substitution, and this substitution right now may seem a little bit arbitrary, but once we go to the end of the solution, you will see why making this substitution. This is your substitution. I don't know how to spell this word. I'm just kidding. There you go. Substitution. This is your substitution. Wt equals v prime t. And so therefore, w prime t is also equal to v double prime t. And so as a result, what we can do is we can rewrite this such that it's w prime t y1 t plus wt 2 y1 prime t plus pt y1 t equals 0. Okay, and then from here, if I bring this onto a new page, from here what we can do is we can bring this to the other side. We can bring this to the other side like so, and we can have w prime t y1 t is equal to minus wt 2 y1 prime t plus pt y1 t equal, or just my bad, doesn't equal 0. Yeah, and then from here, if we divide both sides by y1 t wt, and again y1 t wt, what we end up with is this. So w prime t over wt is equal to minus 2 y1 prime t y1 t, and then this y1 will cancel out with this y1, so minus just pt. And then from here that's your equation now. And what we have to do is we're trying to get a value for w, right? So this probably reminds you of the last video where we did something similar for the Abel's formula, when we were deriving the Abel's formula, but now we're deriving the method of reduction formula. So if this becomes, the left hand side becomes ln of absolute value of wt is equal to minus 2 ln of absolute value of y1t minus the integral of pt dt, right? And then what you want to do from here is, if we raise both sides to the power of e, what we end up with is absolute value of wt is equal to, and I'm just going to bring this negative 2 inside, and that's going to be e to the ln of 1 over y1t squared. And anything that is such that it's e to the ln will just simplify to whatever's in the argument of ln. So we can just rewrite this again as 1 over y1t squared, and then this becomes e to the minus pt dt, like so. So then because we have this absolute value here, this plus this numerator can be a plus or minus, right? So if I get rid, if I do this here, where I get rid of this and this just becomes plus minus, this plus minus 1 I'm going to replace with a, where a is some constant value. Yeah, and this a, this is just because of the formula. I always just personally set the a to 1, okay? So whenever you see this formula, just know that 9 times out of 10, a will indeed equal 1, okay? So this is just convention. I'm not exactly sure why 1 is written as a, but I always just write a as 1. Yeah. Okay. And then so this is now your first step for finding y2 given y1. You find wt, and then your second step is actually this substitution that we did up here. This substitution. So you have to undo the substitution, right? This substitution said that wt equals v prime t. Wt equals v prime t. So we're trying to find vt. So that means this is going to we're going to need the integral of both sides, and that will give us dt. And so then this is just vt is equal to the integral of wt dt. So then therefore vt is the integral of wt dt. And then from here, all we have to do, because remember what we said initially was this. We said that y2 is going to be equivalent to y1 multiplied by some unknown function, right? Now we know what the value of that unknown function is, right? So then all we have to do is we just now have to find y2, and y2 is equal to vt y1t, and there you go. That is how you solve a method of reduction of order. So if I were to summarize this, and I'm going to just bring this out up here. Okay, if I were to summarize this, then this is the method of reduction of order. Okay, and this is for a differential equation that has the form y double prime t plus pt y prime t plus qt yt equals 0. Okay, and we are given y1t. Okay, so these are the steps you have to take to find y2t if you're given y1t. All right, so with that in mind, let's do some examples. So the first example is this. First example is find the second solution. Find the second solution of x minus 1 y double prime x minus x y prime x plus yx equals 0, such that x is greater than 1. And we are also given y1, given y1x, and y1x is equal to e to the x. So in order to solve this, or actually please go ahead and try this out on your own. Remember, these are the steps. So what I'm going to do is I'm just going to steal all this, and I'm going to put it on the next page. Put it on the next page and make it smaller. Make it smaller, like so. Okay, I'm gonna get rid of that box, and then let's put this here, like so. And there you go. So this, I'm gonna put a new box around it. This is your procedure. So please go ahead and try this question out on your own. Okay, I'm hoping that you've tried this question and you've succeeded. Now we're gonna try and do this together. So step one, I should probably get rid of this and just call this an example so that you don't get confused. Sorry. I-E, there you go. Okay, so step one is WT equals a y1t squared e to the minus integral of pt dt, where a is a constant. Okay, and I might just make this even smaller. I'm sorry, it's just taking too much room. There you go. That's better. So this is your WT. So let's find WT. So WT is equal to a over y1, and so this is e to the 2x, right, because we square. And also keep in mind that this is in terms of t, but this differential equation is in terms of x. Okay, so just keep that in mind. And then we have e to the minus your pt, but now remember, this equation needs to be made into standard form. So if we convert this to standard form, we get y double prime minus x over x1, x minus 1, y prime x plus 1 over x minus 1, yx equals 0. And so then your pt as per this standard form is going to be minus x over x minus 1. But this is px actually, because we are talking in terms of x. So here, maybe I'll change this formula so that it's just in terms of x, like so. And so your px is x over x minus 1 dx. Now, if we try and solve this integral right here, we can't really solve this integral in the way that it currently is. So, what can we do? Well, first of all, px is minus x over x minus 1. And so, the integral we're trying to solve, these two negative signs will cancel and we'll just be left with x minus 1 dx. So we're going to have to do some conversion, some kind of trickery to make sure that we can solve this integral. So we can say x minus 1 plus 1 over x minus 1 dx, and then we can split both sides, right? Because I'm just subtracting and adding 1. So I'm just adding 0, and that's allowed. So x minus 1 over x minus 1 plus 1 over x minus 1 dx integral 1 plus 1 over x minus 1 dx integral. And so then this integral is x plus ln absolute value x minus 1. So therefore we can say that WT, and I should change my color, WT is equal to a over, actually I should just say a e to the minus 2x times e, and then we took the integral, and the integral evaluated to x plus ln of absolute value x minus 1. And so then from here, what we can do is we can split it further. So a e to the minus 2x, e to the x, e to the ln x minus 1, like so. and then we know from up here that x is greater than 1. So that means that we can get rid of this absolute value actually, because x is greater than 1. Okay, so that's why we can get rid of the absolute value. And then remember, we can simplify this term to just x minus 1, and then e to the x, e to the minus 2x, a, and then we can add these two powers together to give us e to the minus x, x minus 1. And this is wt, this is wt, this is wt. So that is your wt. Your next step, step 2, is to find vt, which is the integral of wt. Okay, so next step is vt is equal to the integral of wt dt. And so then I'm just going to bring this to a new page. So then what we can do is vt equals, let me put this into yellow again, vt is equal to the integral of I'm going to just bring this a out because a is a constant, right? A element of reals. And then e to the minus x, x minus 1, and then this is in terms of t, and I'm going to change this. So this is x. Oh, whoa, I just realized something. All these w's are in terms of x. All these w's are in terms of x. And so this will also be in terms of x. Okay? All right. So this is dx. And so then this looks like an integration by parts. IBP. Okay? And so integration by parts, we can do this. So let's see, if we take the integral of e to the minus x, x minus 1 dx, remember that IBP looks like this, where v du, I should be clear, v du is equal to uv minus u dv. So we can say, okay, we can say that we have a u and we have a dv. So your u, we can say, is x minus 1, because then du will just equal dx, and dv is equal to e to the minus x, and v is equal to minus e to the minus x, right? Because we take the integral, and so then we get minus e to the minus x. Now we put it into the IBP form, so uv is going to be x minus 1 minus e to the x minus the integral of u, which is x minus 1, and dv, which is just dx. And so then what we can do is we can just solve that integral, and what we get is the integral 1/2 x squared, 1/2 x squared. Sorry, I'm just checking my steps. I don't want to get anything wrong. Oh, wait a minute. v du equals u dv. u dv. What am I doing wrong here? v du. Oh, hold on. Sorry. I think it's u dv equals v du. Yeah, there you go. That's what I was screwing up. So then uv is correct, and then we have to get v. V is minus e to the minus x, and du is just dx. Sorry about that. This is the correct form. I apologize. So minus x minus 1 e to the minus x plus the integral of e to the minus x dx. And this integral is minus e to the minus x once it's evaluated. And then I'm just going to bring this term down. And then if we expand this left term, we get x e to the minus x plus e to the minus x minus e to the minus x. These two terms cancel, and then you're just left with minus x e to the minus x. So then therefore your Vx is equal to minus x e to the minus x. All right? And now we've done step 2. So step 1 and step 2 have been completed, and step 3 is just very easy. And step 3 is just this, right? Step 3 is y2t is equal to vt y1t. And if we write this in terms of x, just to be more clear, v1x, if we write that in terms of x, like so, then what we can do is y2x is equal to vx, and vx is minus x e to the minus x, like so, and y1x all the way up here was e to the x. Okay? So there you go. E to the x. So then from here we can say that we can combine the exponents and we get e to the 0, and e to the 0 equals 1. So therefore y2x just equals minus x. y2x just equals minus x. And there you go. This is your y2. And that you found this solution. Now, in order to verify, this is like an additional step you don't have to do, but it's always a good thing to verify. So we should always try and verify. This was our original differential equation. All right? So if we take this differential equation and then we say, okay, well, I know y2 is a solution, so then y2 prime of x is just minus 1, and y2 double prime of x is just 0, then we get x, we know that y double prime is just 0 if we have the 2, right? And then the second solution, and y2 is negative 1, so negative x minus 1 plus y2 of x is negative x equals 0. And so then this is x minus x equals 0, and this is 0 equals 0. So that's true. This is verified. Okay, this is verified. Yeah. Now let's do another example. And we'll just do one more example and then we'll call it quits. So, second example, solve the differential equation where the differential equation is t y double prime t minus y prime t plus 4t cubed yt equals 0, and we know that t is greater than 0, and we're given that the first solution is sine t squared. And actually, for the first question up here, we know we should try and give you the general solution because that's what the question said. So we know what y2 is, which is y2x equals minus x, and we know that y1x equals e to the x, so therefore y equals c1 e to the x plus c2 minus x, and this is your general solution. Okay, this is your answer. This is how you should express your answer. Sorry about that. Second problem is this. Now we have the first solution and we're trying to find the second solution. So let's copy this let's copy this. Let's bring it down here. And I'm going to try and get rid of these. Perfect. Okay. So, like always, please go ahead and try this out on your own. Okay. I'm assuming you've tried it. I'm assuming you've succeeded. Now you just come back here to check your answers. All right. So, first thing we got to do is we got to put the equation into standard form. So we do that by dividing both sides of the equation by t. So that's 1 over t y prime t plus 4t squared yt equals 0, and t is still greater than 0. And this is in standard form. Okay? And so now we know that your pt is equal to negative 1 over t, like so. All right? And from here we can say that we do the first step, and that is find wt. And again, we just leave the a. And then this becomes sine t squared e to the minus integral of pt, which is negative 1 over t dt, right? And I'm just going to leave the a as 1, or just leave the a as a for now, all right? And so then what we have to do is, let's just bring this sine t squared to the minus 2 to the top, and then we evaluate this integral, and that's just ln of absolute value of t. But remember that t is greater than 0, so then you can write this down as sine t squared minus 2 and absolute value of t. But because t is greater than 0, we can just write this as t. And this is the value of wt. And the nice part is that this time the differential equation was in terms of t. It wasn't in terms of x, unlike last time. And that's a bit of a problem. But it's not too big of a problem. You can work around that, you know? So we got wt, and that's really nice. And then from here, we can further solve this. Oh, and actually, just recall that when you have 1 over sine of x, this is cosecant of x. Okay, so I'm going to rewrite wt as a to the cosecant squared t squared times t. All right, and that is your wt. Now we do the second step, and the second step is this guy, where vt equals the integral of wt dt. So let's do that. So vt equals the integral of at cosecant squared t squared dt. And so now this looks kind of dangerous, because you have to take the integral of a cosecant squared, but it's not too bad. So first thing I'm going to do is bring this a to the outside. All right, and then the second thing that I'm going to do is I'm going to plug in a u substitution. So if I say u equals t squared, I can then say du equals 2t dt. And so then I can say du over 2 equals t dt. And so then as a result, we can express that same integral as cosecant of u over 2 du. All right, and this is a, this is vt, but now it's in terms of u. but we'll quickly resolve this. So now remember what the integral of cosecant was. The integral of cosecant, and I'll write this in pink, was cosecant squared x dx is equal to negative cotan x plus c. Okay, you probably learned this back in like high school or something. All right, and so now we have our integral, and so we can evaluate this, and we can say a over 2, and then we can take the integral of cosecant, and that becomes negative cotan of u plus c, some constant c, and then we continue, and then what we can do is we can put the u as t squared, right? We can put the u as a t squared, which is nice. And then therefore your vt is going to equal negative a over 2 cotan t squared plus ca over 2. And so then this ca over 2, I'm just going to write this as ca over 2 here, ca over 2, and then ca over 2 is equal to b. Okay, so then I'm just going to replace that with b to make life a little bit easier. And then from here we know what that unknown function is, and we know in step 3 we just multiply that unknown function by the original function, which was sine t squared. So then what we can do is step 3, which is y2t is equal to vt y1t. And so your vt can be replaced with this function, this unknown function that we just came up with. And then your y1t was sine t squared. So we can replace that with sine t squared. And that's really cool. So now remember that cotan is actually equal to cosine over sine. So we can rewrite this as minus a over 2 cosine t squared over sine t squared plus b. Okay, and then this is sine t squared. So then your y2t is equal to minus a over 2, and when we multiply the sine to this first guy, the sine will cancel. Okay, the sine will cancel, and you'll just be left with cosine t squared and then b sine t squared, and that is your y2. And so remember that again, y1 was just sine t squared, right? And we have this sine t squared here. So then this looks a lot like a general solution to me, because we have y1, right? And then this y2 is here. So, or I shouldn't say it looks like a general solution. The general solution, remember, is equal to y c1 y1x, or sorry, t plus c2 y2t. And so as a result, y equals c1, and y1 is sine t squared, and c2 of this whole thing. Okay, now this general solution is not wrong, but the thing is, it's a little bit redundant, because notice how we have sine t squared here already. So and this is just C1 is just some constant. And beta is also technically just, or B is also just technically some constant, provided, yeah, B is equal to C over 2. But that doesn't really matter because C could be any constant, right? And we can just say A is 1. So what that means is this is redundant and we don't really need that. And so, or we could be more clear actually, and we could say that C1, and we could combine it. So C1 plus B sine t squared plus C2 minus A over 2 cosine t squared. And you could express it like that. But even this could be simplified, and we could just say that this is a constant, this first term here, and the second term here is also a constant. So we can just call these C1s and A1s. We can just say that A1 equals C1 plus B, and A2 equals C2 minus A over 2 minus A over 2. And so therefore your general solution in its simplest form is sine t squared plus A2 cosine t squared. And so you can see that this is written in the most simplest form. And I know it sounds weird where we just took constants and we made them into other constants, and this might be kind of confusing. But just know that A1 and A2 could be any constants. A1 is an element of the entire real set. A2 is also the element of the entire real set. These could be any numbers. It doesn't matter. So therefore, that's why I wrote it like that. And that's why I don't like this messy kind of way of showing it. The general solution is this, and it's clean, right? This also works, and so does this as the general solution, but they're not very mathematically beautiful, right? They're kind of messy. So with that, on that note, we conclude this video. Thank you for watching. If I could have done anything better, please let me know in the comments down below. Thank you.